Hey guys, so today we're going to be going over the DI method, which is a faster way to do integration by parts. So whenever we have an integral such as x cubed e to the x dx, you guys know that you can do integration by parts and you can apply the integral formula, which is the integral of u dv is equal to uv minus the integral of v du. But the problem about this method is it takes a long time to constantly plug into the formula again and again. So the DI method or the tabular method comes up with a way to do this in a faster way. So what you do is you basically just set up two columns, right? You do D and I. And the D column stands for derivative, the I stands for integral. And you're basically going to put a x cubed, or in this case x cubed because it's going to terminate. And I'll show you what I mean by terminate. So we'll put the x cubed here. And then for the integral side, we're going to put the e to the x. And then at this point, we just basically just want to take the derivative till it goes to 0. So we get 3x squared, 6x, 6, and then 0. And then now it's done because it's hit 0. And then for the integral side, we're going to put in the e to the x's. So now that we've done this, we just basically need to write the answer. And how this works is we need to alternate signs with plus and minus. So plus, minus, plus, minus, plus. And then we're going to pair the things diagonally. So like this. And then to write our answer, we basically just follow the signs and we put the things together. So we're going to have x cubed e to the x minus 3x squared e to the x plus 6x e to the x and then minus 6 e to the x. So then this is basically going to be our answer. So you're probably wondering, okay, like how does this work? Well, basically, we're essentially taking we're finding each du and we're finding each v and we're pairing them together. So this would be a u, and then this would be a v, and then this would be a u, and this would be a v, etc., etc. And then we're basically going to be pairing it together. So if you look at this part, this is the uv part. So if you're wondering where this v du part comes from, well, the v du part is actually going to be the last line. So the last line is always going to be an integral. So we integrate 0 times e to the x dx. And this is basically the v du part. What you'll notice here, though, is that we're going to be integrating 0, which is just going to equal 0. So we can add on a 0 here. So this is a really quick way to figure out an integration by parts question. And the reason why we have the plus minus is because we're minusing an integral, and then we're applying another integration by parts formula. So there's going to be a minus and then another minus for the v du, hence why we alternate signs over here. So that's kind of how you apply the basic DI method. But it gets more complicated when we have something which is not terminating, and I'll show you what I mean by that. Or actually what we could do here is we could actually show what the answer would be if we didn't terminate it. So if we didn't go to 0. So I'm just going to delete this. And we'll see here that we didn't go to 0, so we ended at 6, right? So now our answer would be x cubed e to the x minus 3x squared e to the x plus 6x e to the x. And then remember, the last line is going to be across horizontally, but it's going to be an integral. So the signs, everything is the same. So we add the minus, we integrate 6e to the x dx. And then now we can solve that integral. So you can see here that we're still going to get the same answer. This is going to be 6e to the x, which is what we had earlier. But basically, this is kind of the basics of how the DI method works. So you can use it always. You just have to remember that the last line horizontally is always going to be an integral. So you can see here that we pair up this into an integral. However, a polynomial or some sort of function isn't always going to terminate, right? In this case, we have a polynomial x cubed, and we know that's going to go to 0. So we know the last line is just going to be a 0 term. However, if you get a more complicated term, we're going to use the same DI method, but we can make some modifications. So an example to do that would be e to the x sine x. So we know we want to apply integration by parts here, but we can't really get one to terminate because we know that sine differentiates forever and e to the x differentiates forever. So picking one for d and I doesn't really matter here. They're going to give you the same results. I'm just going to pick e to the x as I, and I'm going to pick 1 as sine. So you're probably wondering, okay, so when do I stop taking my derivatives or integrals? You basically stop when the function repeats itself. So in this case, we're going to have sine x, cosine x, and then negative sine x. So at this point, because we've repeated our function, you see sine has repeated, we can actually start to write our answer. So remember, when it doesn't terminate, the last line is going to be a integral. And remember to add your plus, minus, plus signs. So when we pair it together now, it's going to be sine x, e to the x, minus cosine x, e to the x. And then remember, the last line is going to be a integral. So we minus the integral, which is sine x, e to the x dx. And then what you're going to notice here is that we initially started this integral on this side, and it's actually, we see it on both sides here. So I'm going to put an equal sign, and you can kind of see that if we call this side I, we have an I over here as well. So if we subtract I from, we add I to both sides, we get 2I is equal to sine x e to the x minus cosine x e to the x, and then I is equal to all of that over 2. So the DI method allows you to do integration by parts in a really fast and organized way without having to set up the formulas every time. Just remember to pair things diagonally, and then the last line becomes an integral.